I'm going to end this chapter with a lecture on conditional probability, and then we'll talk about Bayes' formula. In unconditional probability, we did several examples of that earlier because we had a sample space such as rolls of dice and would ask what is the probability of rolling a sum of 7, and we knew how to get the answer by counting the number of ways you could roll a sum of 7 out of 36. But what if we imposed a restriction on the sample space? And that would create what's called a conditional probability. We might still ask for the same probability. For example, what is the probability of rolling a sum of 7 given that the sum is less than 11? So this is the condition. The condition that's given is that the sum is less than 11. Now we only have 33 elements in the sample space because less than 11 takes these 3 away, 6, 5, 5, 6, and 6, 6. But we still have 6 ways to get a sum of 7. So the new probability, instead of being 6 out of 36, would be 6 out of 33, which reduces to 2/11. Those two probabilities, notice, are not the same. They're different. Let's say A is the event of a sum of 7 and B is the event of a sum less than 11. Well, we know the probability of a sum of 7 is 1/6. But what about the conditional probability? What about the probability that we get a sum of 7 given that the sum is less than 11? Well, that probability is actually conditional, and the way we read it is the probability of A given B is 2/11. And to shorten that notation, we put just a vertical bar between A and B. So when you see this, it means the probability of A occurring given the condition B occurred previously. So now, so the notation for the probability of A given B is just this notation. So as I said, the probability of A was just 1/6, but the probability of A given B is 2/11. Here's another example. Suppose you randomly select someone from the state of Texas. Consider 2 questions. What is the probability that the person selected has lung cancer? And what is the probability that the person selected has lung cancer given that the person is a heavy smoker? Well, obviously these two probabilities, we wouldn't expect them to be the same, even though we're asking the same probability. In both, we're asking the probability that they have lung cancer, but in the second one, we're placing a condition or restriction on them. Well, if you look at this, if you look at my diagram over here, let's say that the yellow, the A, is all those people that have lung cancer. And let's say B are all of those that are heavy smokers in the population. Well, if you want to know the probability of someone having lung cancer given that they're heavy smokers, then what you have to do is you have to look at the intersection. So it would be these people in the intersection, and you would divide that. It would be the people in the intersection, but out of the people in B. So it would be those that smoke and have lung cancer out of those that smoke. So the probability of A given B is actually the probability of A intersect B over the probability of B. And so that's a formula that you can remember. Okay? Now, what you could do, you could actually solve this for the probability of A intersect B and get another formula. If you multiplied both sides of this by the probability of B, then over here the probability of B would just cancel, and you'd have the probability of B times the probability of A given B, which is what I have here, equals the probability of A intersect B. Now, since the probability of A intersect B and the probability of B intersect A are the same, then you could interchange the B and the A here. So here you could change the B for A, and then here you change the A for B, and here you change the B for A. So both of these equations are true. So the probability of A intersect B is the probability of B times the probability of A given B, or it could be written as the probability of A times the probability of B given A. Now let's return to our dice problem. Let's find the probability of a sum of 7, given that the sum is less than 11. And let's see if this formula will work out for us. Let's say A is the event of a sum of 7, and B is the event of a sum less than 11. We want to find the probability of A given B. Well, we can see that, let's find the probability of A intersect B. Okay, so these are all the numbers that are in the intersection. So these are the numbers, these are all of the elements that are have a sum of 7 and have a sum less than 11. So these are the 6 numbers. So the probability of that would be 6 out of 36, which is 1/6. Now, B, what's the probability of B? All the values that have a sum less than 11. Well, there's 33 out of 36, or 11/12. So the probability of B would be 11/12. So based on this formula, the probability of A given B should be the probability of A intersect B over the probability of B. Well, probability of A intersect B is 1/6. The probability of B is 11/12. And then if you invert and multiply, you get 1/6 times 12 11ths. And then you can divide 6 into 12 and get 2. So it's 2 out of 11. Okay? So the probability, and if you go back up here where we did it without the formula, you'll see that the probability was indeed 2 out of 11. Okay, so here's an example. Let's go back to our drivers here that we talked about earlier. Okay, let's answer some conditional probabilities. Suppose we select a randomly selected driver from this group. All right, let's look at A. What is the probability that the driver is in the 26 to 39 age group, given they have more than 3 accidents? Okay, well, let's say A is the event they're in the 26 to 39 age group, and B is the event they have more than 3 accidents. So don't we want the probability of A given B? Well, wouldn't that be the probability of A intersect B, which would be A intersect B would be right here, wouldn't it? So the probability of A intersect B would be 25 out of 1,000. Notice I put that on top. And then the probability of B, more than 3 accidents, that would be over here 100 out of 1,000. So it's 25 out of 1,000 over 100 out of 1,000, which is just the same as 25 out of 100, or 0.25. If we wanted the probability that they had 2 to 3 accidents, given that they are in the 18 to 25 age group, then let's say that's C and D. So the probability of C, 2 to 3 accidents, that would be 325 out of 1,000. And then D, let's see, that would be C. Let's see, D, oh, I'm sorry, I don't need C, I need C intersect D. So C intersect D would be 2 to 3 accidents and 18 to 25. So I need the intersection. So that would be, that probability would be 150 out of 1,000. So that would be on top here, C, probability of C intersect D. And then the probability D would simply be 300 out of 1,000, because if you look up D, that's the 18 to 25 group, so that's 300 out of 1,000. So you have 150 out of 1,000 over 300 out of 1,000, which simplifies to 150 out of 300, which is 0.5. And then E would be this, the next one's part C. We want the probability of E given F, where E is 0 to 1 accidents and F is 40 to 45 age group. So let's find E intersect F, 0 to 1 accident and 40 to 45. That looks like it's 250. So 250 is here. And then we need the probability F, the total in 40 to 55, and that's 400. So that's 400 over 1,000. So we have 250 over 1,000 over 400 over 1,000, which is 250 over 400, or 0.65. Now what's interesting, if we flip those around and go the other way, if we want the probability F given E, well, E intersect F and F intersect E are the same thing. So the numerator would still be 250 out of 1,000, but now it would calculate the probability E on the bottom, which was the probability of 0 to 1 accidents, and that's 575 out of 1,000. So the probability on the bottom would be 575 out of 1,000, so you'd have 250 over 575, and that comes out to 0.435. You could have figured this out without the formula, but I really wanted to stress the formula here. Okay, let me show you how we can find the probability of an intersection using a probability tree. Okay, let's say we send 30% of our products to company A and 70% of our products to company B. So here's company A, 30%, 0.3, and it's company B, 70% go to company B. So the probability that we send them to A would be 0.3, the probability we send them to B is 0.7. Now, company A reports that 5% of our products are defective. So if you go to company A, here, A, we have 5% defective, which means 95 are not defective, D prime. And then B reports that 4%. So if we follow the path to B, we have 4% defective and 96% not defective. So if we want to find the probability that a product is sent to company A and defective, basically what we do is we simply multiply these two together. Just multiply this path. So the probability of A and D, just multiply these together and you get 0.15. Okay, because what we're really doing is we're taking, to find the probability A intersect D, we're calculating the probability A and multiplying it by the probability of D given A. See, this is D given that we've followed the path A first. So this is D given A. 0.05 is D given A. So the probability A is 0.3, the probability D given A is 0.05, and multiply, you get 0.015. Now if we want the probability of A intersect D prime, we just multiply this times this, because that would be the probability A times the probability of D prime given A. So we multiply those two together to get that. If we want the probability of B intersect D, then we multiply the B with the D that comes off of it. So that would be the probability of B times probability of D given B. And then if we want the probability of B and D prime, then we go the probability of B times the probability of D prime. So the tree diagram can be helpful. Well, next we could ask, what is the probability that an item is defective? It should just say an item, not and. What's the probability an item is defective? Well, the probability of D must include both ways it could be defective. So I have to figure out the probability of A and D, the probability of B and D, because this would be A and defective, and this would be B and defective. So I have to add those two probabilities together. So A and defective is 0.015, B and defective is 0.028. So add those two together, and you get 0.043, and that will give me the probability that it's defective. Okay, so there it is, 0.043. Now, what is the probability that an item is not defective? Well, again, you got to go both ways to get to not defective. A and not defective, and then add it to B and not defective. So A and not defective is 0.285. B and not defective is 0.672. So add those together, you get 0.957. Now remember, this is the probability of defective, 0.043. This is the probability of not defective. Guess what? When you add those two together, you should get 1, because the probability of defective plus the probability of not defective must equal 1. On the next video, I'll go ahead and do a couple more examples, then I'll get into a formula called Bayes' formula.